of joy. It will be so beautiful. We will love waves. I need a volunteer, but it has to be a girl. Come on up, Imani. Okay, stand next to me. Okay, great. This is Imani. Imani is going to transfer energy from herself to me. Please give me some energy now. Do it. Okay, I was thinking of something else. Like, yeah, please. Dang. Okay, so are you guys okay? What did she just do to me? Good, yeah, she pushed me, but what do we call it in physics land?
Work?
Yeah, she did work on me, right? She exerted a force over a distance. You guys okay with that? Yes. Okay, great. But let's say she doesn't have to happen to be standing next to me. Suppose I need her to give me energy, but I'm standing kind of far away from her. Oh, and by the way, she happens to have that in her hand. Now, what should she do?
Throw the ball.
Please, go for it. You guys okay with that? Now, she didn't do work on me. What kind of energy did this ball have?
Kinetic?
Kinetic energy. She did a transfer of material from her to me. This thing had kinetic energy. It hit me and then gave its energy to me. It did work on me. It made me move. Okay, great. But let's say she wants to do this while still sitting in her chair. So, oh, by the way, give Imani a big hand. So she's sitting in her chair, but she still wants to impart energy to me. Okay. But it just so happens that she's holding one end of this, okay, and I'm holding the other end, okay, and I'm going to hold my arm up, and now, how is Imani going to impart energy to my arm? Do you see how my arm is bucking like a bucking bronco? You guys okay? Because now, what form is the energy she's transferring to me? What form is that? What is she transferring to me?
Spring, potentially?
Oh, yeah, but look at the spring itself. What do you see on that spring? Are you thinking waves? Waves. You guys okay with that? Thank you so much. You're doing a great job. Here, hold your arm up. I'm going to transfer some energy to Imani now. Watch her hand. Okay, do you see? I'm able to get a lot of energy to her as well. But tell me, am I transferring any material? Is any material transferring from me to her? No, not at all. The spring now that we're not putting waves on it, me and Imani, the spring is the same as it was a minute ago. There's no transfer of energy. Did Imani, was she exerting a force on me? No, she was exerting the force on the spring, but not on me. You see, it's a third way to transfer energy, waves. And that's what we're going to be learning about for several weeks now. This new way of transferring energy, which we call waves. Okay? Thanks, Imani. Good job. Okay, so let's learn about these wave things. Okay. Waves. First of all, in this class, we're going to be talking about two types. Two types of waves. The first type is mechanical. Mechanical waves. What distinguishes a mechanical wave is it requires a medium for the wave to travel through. Requires a medium. So for the wave to travel through. So for example, someone tell me, the waves that Imani was sending to me, why are those mechanical waves? Why were these waves that she was sending to me, why do we classify them as mechanical waves?
The spring was the medium?
Yeah, thank you, Imani. The spring was the medium. Her waves had to travel through this spring to reach me. And that's how the energy was transferred. So yeah, the spring is a mechanical wave. Okay? hey, let's talk about some examples of mechanical waves. Number one, of course, wave on a spring, like what Imani and I were doing. Can you think of another example of a mechanical wave?
Really anything? Like
Yeah.
blankets too.
What's that?
I thought about like a blanket.
Okay,
Like,
waves on a blanket. Okay, tell me more here. I'll write that down, even though it's kind of crazy. What else? Waves on what else?
A rope.
What's that?
A rope.
Sure, a wave on a rope or a string. We in physics land, we classify all those type of waves as waves on a string. What else? What's another example of a mechanical wave? As I speak, yes, Sean.
The ocean.
Okay, ocean waves. Beautiful. Yeah. I mean, what's the medium for ocean waves of the ocean? Yes, Cheyenne.
Sound wave.
Yeah, sound waves, right? You're experiencing waves right now. Yeah? Sound waves are mechanical waves. What's this?
What's the one with the again?
This blanket.
Blanket?
No, I didn't want to say she was wrong.
All right.
I mean,
But yeah, it's like wave on a blanket. Like when you and your friend have a blanket and then you make waves on the blanket. Actually, those are kind of freaky. Those are like waves on a membrane. Those are two-dimensional waves. So they actually have their own math associated with them.
That
but-
makes sense.
Yeah, but we're not.
I know it does.
So,
Thank you.
so let me ask you, like several decades ago, there was a movie called Alien with Sigourney Weaver, and the poster for Alien, advertising the movie, would say, "In space, no one can hear you scream." Is that true? Yeah, because sound requires a medium. If someone were to evacuate this room so there was completely no air in the room, then you wouldn't hear a word I was saying, and we'd all be dead. Okay? The second type of wave is one that doesn't require a medium, a wave that can travel through a vacuum. Can someone give me an example of a wave that travels through a vacuum? Yes? Sure, light waves. Absolutely. In fact, I'll just tell you generally, all the electromagnetic waves travel through a vacuum. And so the other type of wave that we're going to be learning about in this class are electromagnetic, or EM waves. Okay? Can travel through a vacuum. They don't require a medium like these mechanical waves do. What's the biggest example in our lives of electromagnetic waves traveling through a vacuum? Yes? Yeah, the sun. Sure, that's a huge example, literally. But of course, it's the whole electromagnetic spectrum. Let's say this is low frequency and this is high frequency, okay? Tell me, what are all the types of electromagnetic waves?
Radio waves.
Yeah, radio waves, those are the lowest frequency. What else?
Microwave.
Okay, microwaves, they're kind of a little subcategory of radio waves, microwaves, but nowadays sometimes they'll actually have microwaves. But when I was growing up, microwaves were just an example of radio waves. But yeah, if you want microwaves, that's fine. What else?
Ultraviolet.
Sure, ultraviolet. What else?
Infrared.
Yeah, infrared. And of course, you guys already said visible light. Okay, so this is visible light, which is visible. Isn't it A?
I.
No.
Is I?
Yeah.
I is right?
Yeah.
All right, great. And so, now I don't know why, evolutionarily, I don't know why we evolved to have eyes that only can see in the visible spectrum. Although we can feel IR, we feel heat. We have, nerves that detect heat. But I just wish evolutionarily we would have evolved to see the entire EM spectrum. That would be really cool.
Crocodiles
'Cause-
can.
What's that?
Crocodiles can.
Are you serious? How? Wait.
They
how
can see.
far?
They can see bits of ultraviolet.
Oh, so they can actually see beyond what we can see. Well, then why crocodiles and not us?
Well, they've been around for a long, long time.
Oh, really? So they have had millions of years
Yeah.
to evolve. Then why aren't crocodiles smart like us?
They have a language.
What's that?
They have a language.
Do they really?
They have a language of 30 different sounds.
Not us.
I didn't know
Why are they
that.
as smart as us?
I'm doing herpetology for a second.
Okay. By the way, visible light. What's the lowest frequency? What color is the lowest frequency of visible light?
Red.
Yeah, red. And then what comes next? And then
Violet.
then sometimes indigo, and then violet. Depends if you like to go Roy G. Biv or Roy G. Bv. You know, some books, leave out indigo. They think that's not really a color.
Oh.
I don't know what they think, but I like Roy G. Biv better than Roy G. Bv. Okay, great. What are we missing here?
X-rays?
Yeah, X-ray and what else?
Gamma?
Yeah, gamma rays. Okay, so those are my electromagnetic waves. There's another type of wave that we actually measured about 2 years ago for the first time in human history. Do you know what special type of wave we measured 2 years ago? It came about because two black holes collided billions of light years away from us.
I read about it. I forgot what it was.
Yeah.
Oh, gravity.
Yeah, good for you. Good for you, Justin. Yeah, gravity. We're not going to talk about gravity waves, but I still think it's amazing that we finally measured gravity waves. You know, Albert Einstein predicted that there would be gravity waves like 100 years ago, and now we finally got an experiment to prove him right. I just thought that was really exciting. I was so excited when that happened. Okay, well, great. So these are the waves we're going to be dealing with, mechanical and electromagnetic. Okay, there's two modes of motion for mechanical waves. Okay. The first type of motion is called transverse. Transverse waves. Here's my spring. I need someone to come up here and be my spring buddy. Who's going to be? Yes, come on up. Just raise your hand, Paul. Too late. You can't put it down. You know, have you ever seen that SpongeBob episode with the bubble buddy? Well, you're like that, only a spring buddy. I take a few steps back. Thank you. Okay, great. So here's a spring, and I'm going to give you an example of a transverse pulse. It's not going to be a wave because it's just one single disturbance. So this is a transverse pulse. You guys okay with that? Here, I can make, if I reduce the tension, I can make it travel slower. Okay, so you'll notice the pulse is traveling to Paul and then reflecting off of him and going back to me. Okay, and you'll notice the pulse is traveling from left to right and right to left. My question is this: what about the particles of the spring itself? And what direction are they moving as this pulse moves by, as the disturbance moves by? What do you say, Logan?
Up and down.
How many people see that it's moving up and down? It is. It becomes more obvious if I send several pulses to him, and then the pulses I send start interfering with the pulses that reflect off of him, and then pretty soon I get something called a standing wave, and that's what I'm getting here, is a standing wave. And now can you see that although the wave is supposedly moving left to right, you know, because that standing wave is just created by a succession of pulses that interfere with each other, but although the standing waves are going from left to right, the particles themselves are moving up and down. Do you believe that? I'm hoping so, because this is an example of a transverse wave. By the way, we're going to learn later that what I'm making on this spring are called standing waves. Like when you pluck a guitar string, you get this fundamental mode of vibration that we call the fundamental frequency, okay? This is the fundamental frequency, but along with the fundamental frequency, you also get the first, and by the way, this is also called the first harmonic, okay? But you also get the second harmonic, and you just be a post, Paul, let me do all this stuff. No, that's okay. You know, so here, because only one of us gets to do this. So this is the second harmonic mode of vibration, or we'd call this the first overtone. This is present on the guitar string when you pluck it, along with that fundamental frequency. And you also get the third harmonic, which is like this, and that's the second overtone, and you get the fourth harmonic and fifth harmonic and so on. All those harmonics are present when you pluck a guitar string, and it's the amplitude of the harmonics that make a guitar string sound different from a banjo string or a violin string. Okay, it's the amplitudes of those harmonics. The fundamental mode of vibration, guitar, banjo, violin, they all look the same. They all look like that. But the amplitudes of the higher harmonics, that's what gives music their sound, their different sound. Okay, thanks a lot. Thank you. Give him a big hand. Nice play. Okay, so that's what I want you to get. And did you put it on my desk? Or you gave it to Leilani? Okay, great. Yeah, you can check it over, and anything he got wrong, just change his answers, and it'll be all good. Okay, transverse wave. The direction of motion of the wave, and sometimes it'll help you to think of it as the disturbance. You know, the direction of motion of the wave is, and let me ask you, what's the relationship with the direction of motion of the wave and the direction of motion of the particles in the medium? Yeah, they're perpendicular. Direction of motion of wave is perpendicular to the direction of motion of the particles in the medium. Okay, those are transverse waves. And so it's very easy to draw a transverse wave. All I have to do is just draw a sine wave. I can draw the type of wave that you saw Paul and me making just a couple minutes ago. There is a transverse wave right there. The wave is traveling this way, the disturbance is traveling this way, but the particles themselves are traveling up and down. Okay. The second mode of motion is longitudinal. Longitudinal waves. Longitudinal waves. I need to give you an example of a longitudinal wave. Slinky. I love slinkies. Okay. Here we go. I'm going to show you a longitudinal wave. You're going to watch that longitudinal wave travel down, hit the bottom, and travel back up. The reflection will travel back up. Are you seeing that? So the wave is traveling down, then it's hitting the bottom and traveling back up. Are you guys okay with that? Well, what's the direction of motion of the coils of the slinky themselves? The disturbance is going up and down. What direction are the coils going? Believe your eyes. What do you say, Noel? Yeah, up and down as well, right? Do you see the direction of motion of the disturbance is in the same direction as the direction of motion of the medium itself? If I wanted to make transverse waves, I could do it. That would be a transverse wave, right? But I'm not making transverse waves. I'm making longitudinal waves. You see? So that's what distinguishes a longitudinal wave. The direction of motion of the disturbance is parallel to the direction of motion of the medium, particles in the medium. You guys okay with that? You believe? Hope you believe. So we do. Oh, am I going to have to sign it?
I just signed it for him.
Yeah, I should teach. Oh, good. Yeah, the teachers don't question it anyway.
No, they really don't.
Yeah, let me see what you signed it. You signed it, Mr. Shana?
No.
Oh, Leilani, baby. You signed it like your name, like you're a student?
Yeah.
All right, let's see if the teacher. Who is your teacher you going to?
Mr. Hall.
Mr. Halls, does he know Leilani?
Yeah.
Just tell him, yeah, what of it, Mr. Hall? She gave me permission. Okay, longitudinal. So the direction of motion of the wave is parallel to the direction of motion of the medium, of the particles in the medium. Okay, so that's it, longitudinal and transverse. Now, it's a lot harder to draw longitudinal waves. Like, how would I draw a longitudinal wave? I would go like this, like here are the wave, oops, I'm not changing the amplitude. These are coils on the spring. I mean, I don't know. Is that looking kind of like longitudinal waves? I don't know. I'm trying to get it so that it's close together, like this is a crest and this is a trough. And then this is a crest. Don't draw this. I'm just showing you. I find it very difficult to draw longitudinal waves. I find it incredibly easy to draw transverse waves. So what's going to happen is when we deal with longitudinal waves, then a lot of times I'm going to actually draw transverse waves to model them, because it's just way easier to draw a transverse wave than to try to fashion some sort of longitudinal wave. Okay? But the fact remains, tell me, what is the most important example of longitudinal waves in your day-to-day life?
Spring?
The spring, you mean like the slinky?
Yeah.
Okay, slinky's good. There's something even more important than the slinky. What else in your lives is longitudinal waves rather than transverse waves?
Sound.
Yeah, good for you, Pooja. Sound. Sound are longitudinal waves. These are compression and decompression waves that come to your ear and expose the outside of your ear to high and low pressure, and that's what makes your eardrum vibrate. But these are longitudinal waves, okay? Other waves are transverse, waves on a string, waves on a spring, ocean waves, although ocean waves are a little bit more complicated, but you can think of them as transverse if you like, okay? So, but longitudinal waves, that's sound. That's the big longitudinal wave. Also, with earthquake, again, I hope I'm right on this, because this is going out on YouTube, and I hate lying on YouTube, but I seem to recall I read about this, that S waves are longitudinal, but P waves S waves are transverse and P waves are longitudinal. By the way, what am I referring to with S and P waves?
Surface waves and then, what's the other one?
Come on, Chris.
Wait.
What? For S and P waves?
Yeah. What did you call the S wave?
Aren't they called surface waves? Or they're
Oh.
known as body waves or something?
Oh, I may have to be wrong. I thought they were secondary. I thought P was primary and S was secondary. And where do we get them?
Well, isn't it as like when an earthquake happens, there's
Yeah.
like it's the first S wave. The S waves are the first like immediate waves that we get, and then like the P waves are the secondary, I think.
Oh my
If I
God.
remember correctly, but I could be wrong.
I might be wrong
No,
then.
no, 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 no.
Anyone watching on YouTube, doubt everything I say, but I thought S meant secondary, P went primary. Longitudinal waves tend to travel faster than transverse waves, so you get the longitudinal wave first and the transverse wave second. But I don't know. What is?
Secondary.
Oh,
What's that?
It says S waves are secondary.
Okay, so I was correct.
Yeah.
They're not surface waves.
Oh, so Chris was totally wrong.
Yeah.
Oh, Chris.
I'm so sorry that Zena had to find out that you were totally wrong. I feel really bad for you.
Oh, at least Mr. Shane is right.
I'm never right. Well, I am right sometimes. I go home, I'm never right. But anyway, that's what I think it is. If anyone reads further, make sure it's longitudinal versus transverse, but I'm not sure. Now I'm doubting myself. Okay, well, great. Hey, that was fun. It is now time to do some math pertaining to waves, and I've been going in slow motion like I always do with you guys. I don't know what my problem is, but here we go. Okay. So I'm standing on a boat. I'm standing on the deck of a boat in the ocean, and I'm looking at all the waves of the water, and I decide, you know what? I'm going to make a graph of the waves of the water, because why not, right? And so I get to my graph paper, and I decide, okay, I'm looking at the waves, all of the waves, and they look like this. Okay? The y-axis is going to be the amplitude of the waves, and that's going to be in meters. And the x-axis is going to be position or distance, because I'm looking at all of them simultaneously. So this is going to be position or distance, and that's going to be in meters. And then I decide to make this measurement from here to there, from the crest of one wave to the crest of the next wave. Tell me, this measurement, what do we call that measurement? Pooja says wavelength. Is anyone thinking period? Okay, great. But what's the units of period?
Seconds per second?
Seconds. Is this have units of seconds?
No.
Heck no. So Pooja was right. You guys okay with that? This is indeed wavelength. Wavelength. The distance from one crest to the next crest is wavelength. That is the length of a wave is wavelength. Okay? Now, wavelength gets to be called by a Greek letter, and that Greek letter is lambda. This Greek letter, we pronounce it lamb, like little cute little baby lamb. Lambda. And that is the distance between two successive crests. Distance between two successive crests, or two successive troughs, or whatever, the one part of a wave and the same part of the next wave. That's your wavelength. But now let's say I decide, you know what, I'm not going to look at all the waves simultaneously. Here, let me get a bit more. I'm not going to look at all the waves simultaneously, no siree. I'm going to go down into the cabin. Here, I'll get on camera. I go down into the cabin, open the door just a crack, and I'm looking at a buoy. And I'm watching this buoy go up and down. I can't see anything else, but I'm looking at this buoy, and it's going up and down. And at this point, I decide, well, I'm going to graph the position of the buoy versus time. So now I'm getting a graph where this is time in seconds, and this is still amplitude. And now I'm graphing the position of the buoy with respect to time. Here, it's at the equilibrium position. A moment later, it's here. A moment later, it's there. A moment later, it's back here, there, then down here, and up. And I'm graphing the amplitude of the buoy with respect to time. And of course, I get another sine wave. I get the same sort of sine wave. But now, this measurement from there to there, that's not wavelength anymore. What is this measurement? Yeah, that's period. So, the question is it period or wavelength? The thing you have to ask is, hey, is this is this amplitude versus position or amplitude versus time? If it's amplitude versus position, it's wavelength. Amplitude versus time, it's period. And someone's got to tell you what it is. The last thing we're going to learn together is a formula, a handy-dandy formula.
Great.
That relates velocity, wavelength, and frequency. And here comes the formula now. I could do some stuff to lead you to the whole formula, so you could have this illusion that you've discovered it for yourself. But I'm not going to do that. I'm just going to tell you what the formula is. I discovered it. Well, no, you didn't really discover it. You just had a teacher who totally led you to it. Here it is. Speed, really it's wave speed equals frequency of the wave times the wavelength. Or to put it really simply, V equals F lambda. Woo. Yes, easily the most important formula you're going to learn from this chapter. V equals F lambda. So here comes my first example. You're at the beach. 5 waves. 5 waves crash into you every every 60 seconds. Distance between 2 successive crests. Distance. Distance between 2 successive crests is 20 meters. Get the wave speed. How fast is that wave going when it crashes into me? I'll give you a hint. Please use this formula. Of these new lollipops, mango is my favorite. Yeah. But I think I like the caramel ones better.
You like the chocolate?
Yeah, I miss chocolate. And I like orange. Orange is my favorite flavor. None of those is as good as orange. Okay. V equals frequency, 5 waves or 5 cycles per 60 seconds. And then the lambda is, what is it, 20 meters? So I get a velocity of 5/3. How many people got 5/3? Yay for each and every one of you. And tell me, what's the units?
Meters per second?
Yeah, because there's the meters and there's the seconds. So if you don't remember the formula, hey, you can always just look at the units. And waves is unitless, so it's meters per second. Yay. Okay. Let me see if there's one more thing I want to talk about. Yeah, I think I'm going to do this here. 570 on the AM dial, KLAC. Do you know what the 570 stands for?
The amplitude?
What is the, what's that?
The amplitude?
Nope, not the amplitude,
Frequency?
not the wavelength. Who said frequency? Yeah, frequency. Thank you. That's what the number on your radio dial stands for, is frequency. For example, KLAC, which is sports talk radio I like to listen to, that's 570 kilohertz. That's the frequency. Tell me, these are radio waves, so how fast do radio waves travel? What's that? No, radio waves travel fast. Just like any other electromagnetic wave, how fast do they travel? Yeah, speed of light. Yeah, so the speed of this wave is 3 times 10 to the 8th meters per second, correct? And so I can get the wavelength of KLAC. The wavelength is going to be V over F, which is 3 times 10 to the 8th meters per second over 570 times 10 to the 3rd hertz. And this ends up being approximately 526 meters. So when you were thinking slow, you were thinking because it has such a big wavelength. Yeah, so that's KLAC. But how about FM 106.7, KROQ, KROQ? First of all, does anyone in this class actually listen to KROQ? Oh, good for you guys, okay. Now, I have to share with you guys, like, 25 or 30 years ago, literally half the class would have raised their hand. KROQ was the station. They played new wave music, and all the kids listened to it. It was awesome. But now, music sucks. But anyway, here we go. And this is going to be 106.7 megahertz. That's the thing that characterizes FM. It's much higher frequency. So the wavelength of K-Rock is 3 times 10 to the 8th meters per second over 106.7 times 10 to the 6th hertz, which ends up being 2.8 meters. Now, if the bell rings, don't leave, because I'm doing this to point out one thing. Let's say you're in a parking garage and you've got your radio on in the parking garage. Here's your antenna. And let's say the parking garage is approximately 3 meters high. Have you experienced this? Which band do you lose? Which becomes staticky, the AM or the FM? How many people say the AM becomes staticky? How many people say the FM? Okay, believe it or not, it's the AM. Next time you're in the Montclair Plaza or Disneyland or in a gas station with one of those awnings, check out AM versus FM. You're going to find that the AM gets totally staticky and the FM is clear as a bell. You don't lose the FM, you lose the AM. Why do you suppose you lose the AM but not the FM? Here's the wavelength of the FM. Here's the wavelength of the AM. You know, that's the wave of the AM. Which of these is going to fit in this opening more easily? Yeah, the FM. Try it sometime. Yeah, you don't lose the FM because it's got a much smaller wavelength. The wavelength fits in the opening. Now, I'll elaborate on it later when we learn about diffraction, but for now it's enough to know it fits. FM fits. All right, good luck, you guys. Thank you.